Greetings. Welcome back. Today what I want to do, we started talking about differential equations, especially first order differential equations, and I want to give you a sense for how things work and how looking at structure can, looking at how a differential equation is built, how that might lead to ways of solving. So I want to present to you two and compare these two. So this is a little talk on two first order differential equations. And I want to bring in this idea of a general solution and a particular solution to these kind of things. So let's compare the following. The first differential equation is dy dx equals x minus e to the x over 2. Now I brought that one up recently in another video, but now I want to take a bit of a deeper dive to see how this guy works. The other guy is dp dt equals p over 2 minus 450. Now in this first guy, the independent variable is x. The dependent variable, the unknown function, the mathematical model, y of x, is y. In this particular guy, t again, t is the independent variable, and p, some function that has something to do with some word that starts with p, it turns out it's population, is the dependent variable, is the unknown function, is the mathematical model in this case. So what I want to do is I want to start with this guy and mess with that one. But first, let's take a look at some things that are the same for both. Both these differential equations are first order. And that should be relatively straightforward to see. The unknown function, the independent variable is x, the unknown function is y, and there's a first derivative of y with respect to x and no other derivatives. So this guy is definitely first order. Same thing here. This guy is definitely first order because the only derivative we see is dp dt, and that's the first derivative of the unknown function p as a function of t. And they both are linear. Now again, here, this is y prime. Its coefficient is 1. This guy, there is no y in this entire equation, the unknown function. Its derivative is there, so we have to worry about that. We still have to solve for the y, but the function that is not attached to any of the variables y or y prime is this x minus e to the x over 2, which is a function of x. That's nonlinear, but this is still linear as a differential equation. This guy's a little bit easier to see. The coefficient in front of dp dt is 1. The coefficient in front of p is 1/2. The thing left over by itself is 450. Okay, minus 450. So that one's pretty easy to see that it's also linear. So both of these guys are first order differential equations, and they're both linear. A has a particular form to it. Y prime equals some function of just x. And this guy is the independent variable. And that gives us an insight as to what this differential equation, as to maybe how we might solve this differential equation. The fact that the right-hand side does not include y actually works in our favor. This becomes really just a calculus course, calculus problem. Okay, here, and this is just calculus. Right? First semester calculus. In essence, this differential equation is telling us find a function y whose derivative is x minus e to the x over 2. So you're finding the antiderivative. In essence, y of x equals the antiderivative of x minus e to the x over 2 dx. What's kind of funny is that this guy has a name. If these are called differential equations, you can guess what this is called. It's called an integral equation. And in essence, these are the two same equation because they're giving really the same information. Okay, so that's this one. And you remember, finding an antiderivative of a function, if they're elementary functions like these guys, or sums or products, or differences, then it's usually not so bad. So we can solve this guy. via integration, I can find this antiderivative. And what I wind up with is y of x equals x squared over 2 minus 2 e to the x over 2. And this is a general antiderivative, right? You're finding an antiderivative. So there's a lot of particular antiderivatives. I need to add an unknown constant here because I don't know which function I have. I have to sort of list them all. Okay? And we know from taking an antiderivative that all antiderivatives differ only by a constant in this particular case. So we're left with this thing. And we can go from there into a definition. And that definition is a general solution to a first order ODE is an expression encompassing all solutions to the differential equation. Some way to write every solution in one expression is called the general solution to a differential equation. Now, if you're given a differential equation like this, it's a matter of just integrating. Even this guy will find that there's a way to write it, a general solution. In terms of using an unknown constant. In this particular case, it's just added on, but it's not always that way. It can be a little bit more complicated, which we'll see when we actually solve this guy. But that's called the general solution. Now, it's also called other names. It's also called a one-parameter family of solutions. Okay, and I'll use this term a fair amount because this is an entire family of solutions, but they all differ by just this constant. This constant becomes a parameter, and if I choose different values of that constant, I wind up with getting different solutions, basically. Now, in this particular case, because that constant is additive, if I want to graph this solution would live in the xy plane. Okay. And I can choose a value of c and then graph this guy because it's just a function y of x. I can choose different values of c. And one thing you'll notice is that all of these solutions, well, I'll do them in this color, it's fine. They kind of look like this. Oops, that really should go like that. If I drew well, they're all just vertical translates of each other. And this would correspond to different values of c. For instance, let's say I put this guy here, and this corresponds to the particular function where if I stick in 0 for x, I get 1. Okay, so this is the value 1 in this particular case. And that corresponds to this particular curve. Actually, I like this color. That corresponds to this particular curve. And that particular curve actually corresponds to c equals, do I want a plus or a minus here? I want a plus, 3, right? Because if I stick in 0 here, I get a 0 here. If I stick in 0 here, I get 1 here. So this is minus 2. And then I need a plus 3 to get me to 1. Okay, so that corresponds to c equals 3. So in essence, I can say that y of x equals x squared over 2 minus 2e to the x over 2 plus 3 solves a for y of 0 equals 1. Okay. And that allows me to draw my particular curve, but the general solution is not. The general solution is an entire family of curves, and this guy here becomes the general solution to this particular differential equation. And that's enough for now, basically defining what a general solution is. The next video, we'll be talking about what a particular solution is, and that will lead us to a way of describing a differential equation that might have some initial data to it, called an initial value problem. So I'll leave you this for now. Thank you for listening, and we will talk again very, very soon.